Now in this module we will study precisely what are vectors and the collection of all vectors at one point known as the tangent space. Now this is our first module where we are going to develop our tools that will help us in understanding shapes of curves and surfaces in R3. Now the use of vectors in understanding the geometry of shapes is not a new concept for us. So for example, when in calculus, when we want to find out the maximum and minimum value of a function, then we use this, for example, first derivative test. So in this first derivative we talk about the derivative of a function, which is basically the slope of a tangent line, not the whole tangent line, just a very one aspect of this tangent line, which is its slope. So just using one aspect or one tiny bit of information about tangent vectors, we can talk about the maximum and minimum value of a function, so which is basically a geometrical property. So that's how important these vectors are in understanding different geometries in R3, for example. Now we will be discussing in future different vectors associated to curves and surfaces as well. So it is very important to define what should be a vector, what should be a precise definition of vector in R3. Now when we talk about R3, then a very usual definition, a very rough way of defining a vector is it is a quantity that has magnitude as well as direction. So that's how we define a vector quantity, and a vector is basically an arrow which represents that vector quantity, which has the same direction as that vector quantity, and it has magnitude as well. So what is a vector then? It has direction and magnitude. Okay, so direction and magnitude. So that's what we have been using as a definition of vector. Now let's see why this description of vector is not sufficient. Okay, now consider this vector A, this vector B, and this vector C in the coordinate plane. Now this vector A and B, they have the same direction and same magnitude. So according to this definition, which says that a vector has a magnitude and direction, this vector A is equal to B, and similarly this vector C has the same direction and magnitude, so A is equal to B is equal to C. So all of these three vectors are equal. In other words, translation of vector does not change the vector. But let's see, consider a very physical phenomena where translation of vector has different effect. So for example, consider this lever. So it is based on this point, and we have a force with this magnitude and this direction, and it is acting at this point, let's say P. Now if we translate this force and move it to some other point along this lever, so the same force, as you can easily imagine, that the same force will have a different effect. So this definition of vector, which says that it has magnitude and direction, is kind of flawed, for example, in this very simple physical phenomena. So what should be added? Okay, so that's a little question for you to think about. So what should we add in this definition of vector so that it becomes precise? And from this very simple situation, we can easily see that by just adding the point of application of this force, we can precisely define the difference between the effect of these two force vectors. So that's what we are exactly going to do. So to define the vector, we mention the starting point of the vector as well, and that's what we are going to do for the rest of the discussion in differential geometry, that our vector is basically P plus V, where P is the point of application, basically initial point of the vector, and V is basically the vector part. Okay, now let's try to understand this definition. Okay, now a tangent vector Vp to R3 consists of 2 points of R3, its vector part V and point of application. Okay, so every vector in R3 is known as the tangent vector. Okay, so what is this definition mean? Okay, so let's say we have this vector v. Okay, now this vector v is different from this vector v. Okay, because this vector v has 0 or origin as point of application, and this vector v has p as point of application. And according to this definition, take any point in R3 and take any vector, let's say w, and let's say this point is q, then this wq is basically a tangent vector. Now there might be one main confusion about this definition, that it doesn't matches with our definition of tangent vector, for example from calculus. Now we will see the connection between these two definitions. So kind of the idea is that in space you consider all the vectors, and when you want to discuss, for example, a curve in the space, then you restrict all of these vectors to one curve. But then of course when we take all of the vectors in R3, then we impose conditions on those vectors. So for example, we say that okay, consider now those vectors satisfying this condition, and now consider those vectors satisfying some other conditions. Now under these conditions, and after restricting all of these vectors to curves, you will be able to get, for example, the usual tangent vector that you understand and deal with from calculus. Okay, so that is the main confusion about this definition of tangent vector. Okay, so anyway, so we have this tangent vector Vp. So any point, take any point in R3, that is the point of application, and take any vector part. So how do we take the vector part? Just take this vector with point of application origin and translate that vector to that point, then you will be getting this vector, for example Vq. So V is the vector part and q is the point of application. So let me make this vector look like that vector v. So this is vq. Now v is the vector part, q is the point of application. Now the same translation of this vector to the origin is going to be v0, and this vector is vp. So vector part is the same, but point of application is different, and this is different from our definition of vector. For example, in our previous calculus courses. Now in this, according to this definition, all of these three vectors are different, and the translation of vector does change the vectors from now on. Okay, so a tangent vector Vp is a vector, basically an arrow from the point P to the point P plus V. Okay, so P is the initial point and the final point has the coordinates P plus V. Let's consider this very simple example where we want to find the geometry of this vector Vp. So vector part is 2, 3, 2 and the point of application is 1, 1, 3. Now we want to know that, for example, what is the initial point? Of course, the initial point is going to be P, which is 1, 1, 3. So this point is 1, 1, 3, the point of application. And the vector part is 2, 3, 2. So what do we do in this case? So we consider this vector part. Okay, so let's say this this v. So the arrow is basically 2, 3, 2, and in the next stage, okay, so let me complete this vector. So 2, 3, 2. In the next stage, what do we do? So we translate this vector to this point such that the point of application is not origin anymore, the point of application is P, and after this translation, this arrowhead has the coordinates P plus V, which we can easily calculate, for example, using head to tail rule. So this Vp is a tangent vector from 1, 1, 3 to the point 3, 4, 5, and 3, 4, 5 is obtained by adding P plus V. Okay, so P is basically 1, 1, 3 and V is 2, 3, 2, which is basically 3, 4, 5. Just add them, and this is the arrow. These are the coordinates of the arrowhead. Okay, so that's kind of procedure if you want to actually calculate the initial and final points of any tangent vector. Of course, two vectors are parallel if and only if their vector parts are equal. Okay, so over here we can see that this Vp vector is parallel to this Vq vector but they are not equal, of course, because their point of application is different. And two tangent vectors are equal if and only if their vector parts are equal and their point of applications are equal. And of course, the vectors are different if their point of applications are different. Now we have three quantities involved for a vector. We have the magnitude, direction, and the point of application. Now at any point P, we can talk about the set of all vectors at that point P, and it is denoted as Tp of R3, and it is called the tangent space of R3 at point P. Okay, so now point P is important because we are calculating or collecting all the vectors at point P. R3 is important because sometimes we can also restrict our structure to, for example, to some surface or to some curve, and then in that case we will be talking about, for example, the collection of all vectors at point P to, for example, that surface. Okay, and in that case the answer would be different. Okay, but in this case we are only talking about the tangent space at point P of R3. Okay, so this is the main structure in which we are working. Now each point of R3 has its own tangent space, of course, and for example, if you are at some other point, let's say Q, then all of these vectors are different from all of the vectors at point P, because these vectors, let's say VQ, WQ, okay, so UQ, so all of these vectors have point of application Q, and all of these vectors, for example, VP, WP and UP, so all of these vectors have point of application P. So all of these vectors are different from all of these vectors. Now the next question is, how many vectors, or can we quantify the collection of all vectors at point P? So that is our next question. So to understand that question, we need to explore addition and scalar multiplication in tangent space at any point. Now before this discussion, or previous definition of vector, which only involves direction and magnitude, we can use a head to tail rule and we can add vectors, but in our current definition the point of application is also involved. Now we will use our previous way of adding two vectors and scalar multiplication of a vector with a scalar, and we are going to use that to define addition and scalar multiplication in the tangent space at a point, and that will help us in quantifying for example the tangent space at a point. Of course we are going to see that it's basically a three-dimensional vector space isomorphic to R3, so that is our main goal that we are going to achieve. So to achieve that, we use addition and scalar multiplication, and we use this to define the addition of two vectors in a tangent space. So VP, WP are two vectors in the tangent space at point R3, at point P of R3. So we can add them in the following way. So in the first step, just forget about the point of application and just add V and W like we added before, by just using, for example, head to tail rule or parallelogram law. Okay, and then include this point of application. Okay, so in this definition, by using this definition, we cannot add two vectors if their points of application are different, which kind of makes sense in the physical scenario as well, because if you are adding force at two different points, then it doesn't make sense that what is the resultant of that force, because they are acting at different points. So you can only talk about the resultant of a force if you are acting at the same point, and that's what this result says, that if your point of application is not the same, we are not allowed to add the vectors. And similarly for the scalar multiplication, that we can scalar multiply a scalar with a vector VP. So what do? We just multiply the vector part with C, just how we did that, and then add the point of application in the second stage. Okay, so using that, we can prove that this tangent space at point P to R3 is a vector space under the above addition and scalar multiplication. Now I am leaving this as an exercise for you to show that this is a vector space. So it satisfies all the conditions of a vector space. It's an abelian group under this addition, and further 3 or 4 conditions are satisfied. Now once again the problem is the same. We want to find how many vectors are there in a tangent space at point P in R3. So once again, to quantify that thing or to prove that this is isomorphic to R3 and it has the same dimension as R3, hence we want to show that TP of R3 is isomorphic to R3, and to show isomorphism we need to recall this definition of isomorphism. So a function or a transformation from vector space V to W is linear transformation if it satisfies the two conditions. It preserves the addition and scalar multiplication, and of course it is a bijective map, and two vector spaces are said to be isomorphic if there exists a bijective linear transformation between them. So what do we need to prove? We need to prove that this tangent space TP of R3 is isomorphic to R3. Now the idea is very simple. The map L from TP of R3 to R3 can be easily defined as L Vp is equal to V. Okay, so using this definition, it's a very trivial exercise to show that this function is an isomorphism, and hence TP of R3 is isomorphic to R3. So in other words, we can say that how many vectors are there in TP of R3. So that is equivalent to how the number of points in R3. So given any point in R3, okay, so let's choose this random point in R3. We can sketch this vector, okay, so with the point of application origin, and this is the head. Let's say it has coordinates A, B, C. Then we can move this vector to the point P, okay, so which is a random point. So any point A, B, C in R3 will give a vector from origin to that point, and we can shift that vector to the point P. So hence this result that given any point in R3, this will give us a vector in the tangent space TP of R3. This is the end of our discussion on tangent space. In this module, we define precisely what are vectors, and these are the quantities that have magnitude, direction, and point of application. And most importantly, we have proved that the collection of all tangent vectors at a point P, they form a vector space which is isomorphic to R3. And this gives us an important hint to deal with the vectors in a tangent space. So the study of vectors in a tangent space at a point P is going to be very parallel to our study of vectors in R3. So in R3 we have ijk's, so that's why in TP of R3 we need to find its own version of ijk. So that's going to be the part of our next discussion.